Bismillahirrahmanirrahim. Dear students, this is Inorganic Material Chemistry Chem 3115 course, and today we are going to discuss second part of sputtering 2. In previous lecture we have discussed introduction about sputtering, and in this lecture we will see the more definitions in sputtering. The basic key concepts of this lecture, as I have already mentioned, we have discussed sputtering in previous lecture. In this lecture we will discuss about basic mechanism of sputtering, sputter deposition, re-sputtering process, the factors affecting sputtering, primary and secondary knock-on procedures, reasons for sputtering, requirements, steps for sputtering, unique characteristics of this procedure, then advantages and disadvantages of sputtering. So starting from the basic mechanism of sputtering, we will take an example to understand the sputtering procedure. So for example, we consider we have an evacuated block which is attached with the vacuum power. The vacuum power is used to create the vacuum to evacuate the block. So the evacuated block, it has a vacuum power. This vacuum is created at 10 raised to power minus 5 to 10 raised to power minus 6 torr. So the vacuum is created by using the vacuum power to attain a very low pressure inside the box. So inside the box, substrate is attached at the lower side. The substrate and block are grounded so that extra charge transfer to the ground. The substrate is the material on which we will deposit a thin film. On the other hand, the target material, which is also called the source material, made up of titanium, is isolated from the block. Target material is negatively charged and acts as cathode. Due to negative charge on cathode target material, the positive ions, in other words the cations, will be attracted towards the material cathode. Target material is also attached to the grounded power supply. So the substrate is grounded to the power supply and target material is also grounded to the power supply. The target material is negatively charged and it acts as cathode, while the substrate is positively charged and it acts as anode. When argon gas is entered in a measured quantity in an evacuated block, it becomes ionized immediately. The ionization of argon is due to flow of electrons from cathode to anode. Cathode is negatively charged, so it ejects electrons and these electrons move toward positively charged anodes. The argon gas is ionized by the flow of these electrons. So these electrons acts as primary electrons that strike with the argon atoms and ionize the argon atoms. In this equation we can see the argon strikes with primary electrons, or primary electrons strike with argon. Argon cations are formed and electrons are ejected from this argon, and these electrons are called secondary electron. So the electrons ejected from this organ, these are secondary electrons. So the electrons move towards anode, which is positively charged, while the argon ions strike to the cathode source or target material with high energy and sputter the atoms from the target. These sputtered atoms strike to the substrate placed in the front of the target and deposit on it. In this way, the deposition of thin film takes place by sputtering. Here is a schematic diagram of the whole procedure. We have a block. This is a rectangular block. We use vacuum supply to evacuate this block to attain the pressure 10 raised to power minus 5 to 10 raised to power minus 6 torr. A cathode which is negatively charged and an anode which is positively charged. The cathode is made up of target material, for example titanium here. Anode is made up of substrate material on which the target material has to be deposited. Both of the electrodes, cathode and anode, they are grounded to the power supply. From one side, argon is entered into the evacuated block in measured quantity. So the electrons which are moving from cathode to anode, they strike with argon and ionizes argon, plus secondary electrons are formed. So these argon ions, they strike with the cathode which is negatively charged. These are attractive towards the negatively charged cathode, and when they strike the cathode, the atoms or the ions of target material, they are ejected and they move towards the anode which is substrate, and they are deposited on the surface of anode, and a thin layer is formed on the surface of anode. So this is the basic mechanism of sputtering and sputter deposition process. So sputter deposition. When an energetic particle strikes a surface of the target material, a plum of material is released. It is just like a shower of sand when a golf ball lands in the bunker. So when a golf ball lands in the bunker, we can see a shower of sand is produced. So this effect is known as sputtering and is used to produce films of materials as thin films as just a few millionth of a millimeter. The source of the ion might either be a local plasma, diode, or planar sputtering mechanism they use local plasma or a separate ion beam source, ion beam deposition. In this picture we can see that the argon cations, they are created by the target material. The target or source material which is cathode and it is negatively charged. The electrons move from cathode to anode, and these electrons, while during their path, they strike with argon atoms, and more electrons are removed from argon atoms and they are converted to argon cations. And these argon cations, they strike the same cathode material from which the primary electrons are ejected. They strike the same cathode material and they sputter the target atoms from this cathode material. So this is a circular procedure that electrons are ejected from the cathode and they ionize the argon atoms and the argon cations again strike the same cathode material to eject the atoms to sputter the target atoms. Sputter deposition is a physical vapor deposition method of thin film deposition by sputtering, in which high purity source material called a cathode or target material is subjected to a plasma gas. And the plasma gas we have already mentioned, it is typically argon. The energetic atoms of plasma gas, they collide with target material and knock off source atoms, which then travel to the substrate and condense into a thin film. So this involves ejecting material from a target, that is a source, onto the substrate such as silicon wafer. Resputtering is re-emission of the deposited material during the deposition process by ion or atom bombardment. Sputtered atoms ejected from the target, they have wide energy distribution, typically up to tens of electron volts. The sputtered ions, typically only a small fraction of the ejected particles are ionized, on the order of 1%. So it means when the atoms are sputtered, they may be converted into the ions by the bombardment of plasma cations, but their quantity is very less, on the order of 1%. So they can ballistically fly from the target in straight lines and impact energetically on the substrate or vacuum chamber, causing resputtering. So normally in sputter deposition, the neutral target atoms or source atoms, they are ejected from the target and they are deposited on the surface of the anode substrate. So instead of sputtered atoms, sputter ions can also be produced. And these ions, they act just like the plasma gas ions which strike to the cathode and eject atoms. Similarly, these ions, which are sputtered ions, they also fly from the target and energetically strike to the substrate where the sputter deposition has been carried out, and they will cause to remove the atoms which are present on the thin film on the surface of the substrate, and this process will be resputtering. Alternatively, at higher gas pressures, the ions collide with the gas atoms that act as a moderator and move diffusively, reaching the substrate or vacuum chamber wall and condensing after undergoing a random walk. So sputtering is widely used and highly versatile vacuum locating system used for the deposition of variety of coating materials. In this figure, here is an example that we are using an argon gas as a sputtering gas, and in addition we are using oxygen. So it is an example of reactive sputtering. We will discuss about reactive sputtering in detail later. So here we can see the sputtering gas, it strikes with the cathode sputtering target. The metal atoms, they are coming from the cathode sputtering target and they react with the oxygen, and metal oxide is formed which is deposited on the surface of the substrate. So this is an example of reactive sputtering. In this procedure, the thin film which is grown on the surface of the substrate, it is not only the metal atoms but the metal oxides which are produced by the reaction of metal atoms with the oxygen which is provided in addition to the argon gas. The entire range from high energy ballistic impact to low energy thermalized motion is accessible by changing the background gas pressure. The sputtering gas is often an inert gas such as argon. For efficient momentum transfer means the transfer of momentum from the sputtering gas to the target material. The efficient momentum transfer, the atomic weight of the sputtering gas should be close to the atomic weight of the target. So for sputtering light elements, neon is preferable, while for heavy elements, krypton or xenon are used. Reactive gases can also be used to sputter compounds as have been shown on previous page as an example of metal oxide. So here oxygen is a reactive gas. The reactive gases can also be used to sputter compounds. The compound can be formed on the target surface, in flight, or on the substrate depending on the process parameters. So the compound can be formed at three places. It can be formed just on the surface of the target, or it can be formed during the flight from the target to the substrate, or it can be produced on the surface of the substrate. So all of these depend upon the process parameters. The availability of many parameters that control sputter deposition make it a complex process, but also allow experts a large degree of control over the growth and microstructure of thin film. Resputtering, as have already been discussed, it involves re-emission of material. For example, silicon oxide deposited by sputtering during the deposition. Similar to sputtering, the re-emission is caused by ion bombardment of the deposited materials. As I have already mentioned, when the noble gas plasma strikes the target material ejects atoms as well as 1% of ions. So these ions, they strike with the deposited material and the deposited material is sputtered off. This process is called. Next are the factors affecting on sputtering. These factors have already been discussed in sputtering yield. We will discuss them in more detail here. Number one is the distance between target and the substrate. Number two, energy of sputtered atoms, angle of incident of sputtered gas, and mass of sputtered material. Distance between target and the substrate. The distance between substrate and target greatly affect on the rate of sputtering. As the distance increases, the sputtered atoms take more time to reach the substrate, thus their energy greatly reduces due to their collision with other atoms. The sputtered atoms are unable to adhere on substrate surface if the distance between the target and the substrate is very large. The sputtered atoms move towards target and deposit on it if the distance between the target and the substrate is not very large. So it is very necessary that the distance between the target and substrate should be reasonable so that the target atoms can be deposited on the substrate. Next one is the energy of sputtered atoms. When the ionized gas strikes the surface of the target material, the sputtered atoms are ejected. As the energy of the sputtered atoms decreases, the process of re-sputtering starts. and sputtered atoms unable to deposit on the substrate surface. So energy of sputtered atoms, it directly relates to the rate of deposition. Next one is the angle of incidence of ionized gas. The angle of incidence of ionized gas is directly related to the sputtering. If the incident gas ions strike at an angle between 60 to 70, then the rate of sputtering, rate of ejection of atoms from the surface of the target will be very high. As we move from 70 to 90 degree, then the rate again decreases, and at 90 degree it might become equal to 0. The rate of deposition is enhanced at this angle from 60 to 70 degree. Number 4 is the mass of sputtered atoms. As the mass of sputtered atoms increases, their speed slows down and their energy decreases continuously. So due to decrease in energy, the process of resputtering starts, hence the rate of deposition decreases. So the atoms of target material, if they have less mass, they will be preferably deposited as thin films on the substrate surface. Next is another phenomena, primary and secondary knock-on. When an argon ion strikes to the target, the first atom ejected from the target, reflected, and then again strike to the target. The target atom sputter from the surface. The sputtering of atom from target material during this reflection process is called primary knock-on. Here we can see this is the argon cation. It strikes to the surface of a target material, and the target material is reflected back and an atom is sputtered from the surface. So this is a circular path, and this process is called primary knock-on. On the other hand, when second atom gain energy from the incoming argon ion and adjacent atom, the adjacent atom also sputter even due to low energy. This is called low energy or secondary knock-on. So here this is secondary or low energy knock-on, in which the adjacent atom, this atom is sputtered off. So these are two processes, primary and secondary knock-ons. Here are some reasons for sputtering. Use of large area targets, which gives uniform thickness over the wafer. Control the thickness by deposition, time and other parameters. Even materials with very high melting points are easily sputtered, and sputtered films typically have a better adhesion on the substrate. Sputtering can be performed from top to down. This is a basic model, that at the top we have a source which is in the form of solid. Here we use a solid. It can be liquid, but usually it is solid. Evaporation can be occur. So this evaporation, it is actually the physical evaporation method. But on the other hand, in sputtering, we have target which is at the top. The plasma strikes to the target, and the target atoms are sputtered off and they are deposited on the surface of the substrate. So this is basic model from top to down. Next are the requirements for the sputter deposition. We need a vacuum, inert gas, power supply and sputtering gas. The steps for sputtering: ions are generated and directed at a target. the ions sputter target atoms, the ejected atoms are transported to the substrate and atoms condense and a thin film is formed. Unique characteristics of sputtering. Uniform thickness over large area of the target material will give a very good thin film. So the simple thickness control is very necessary. The alloy composition maintains stoichiometry with the original target composition. Deposition rates do not differ a great deal from one material to another material. Sputtering cleaning prior to initiating film deposition is very important. The surface is not again exposed to ambient after such cleaning, so that the surface may not be poisoned. The lifetime of a sputtering target may be as long as hundreds of runs and is seldom less than 20. To understand the sputtering more, I have also added a video at the end of this lecture. The students may see this video and they can get more information about the sputter deposition. So this is all about this lecture. Thank you very much.
So exactly how does the sputtering process work? First, your coating materials are placed on a magnetron in a solid form called a target. For highly pure coatings, you need a clean environment with only materials of your choosing. This is why the chamber is evacuated, to remove almost every molecule from the chamber. Then, the chamber is backfilled with a process gas. Process gas species are chosen based on the type of material to be deposited. Common process gases include argon, oxygen, and nitrogen. Now the conditions inside of the chamber are ready to begin the process. A negative electrical potential is applied to the magnetron, which is the cathode, and the ground reference is the chamber, which is the anode. This electrical potential will cause free electrons to accelerate away from the magnetron. When these electrons collide with a process gas atom, they strip the gas atom of an electron, creating a positively charged process gas ion. The positively charged ion is accelerated towards the magnetron. This ion carries enough energy with it to knock off some of the magnetron's target material. This target material will then collect on surfaces in the path the magnetron is directed at. This is how material collects on your substrate. The positively charged ions will recombine with free electrons to create a neutral atom again. The light from the plasma is created when the ions recombine with free electrons into a lower energy state. When a free electron recombines with an ion, it has a voltage. The ion needs less voltage, so this excess voltage is let off in a light. The light is the plasma glow that is seen during processing. This process repeats at a constant rate until the desired thickness is achieved and power is removed from the cathode. This amazing atomic reaction is what makes Semicore a leader in custom vacuum equipment.